morning, everyone. Can you hear me? If you can confirm, everybody. Yeah, okay, perfect. Okay, if you can, anyone else join with the video, that would be great. I know some of you people cannot join us today because of the electricity problems and other problems. It's been a difficult day in Ukraine. Also for me, my father is in Zaporizhia, so he's alive, he's okay. So yeah. So thank you everyone who is joining us. If you're watching us offline, we're here with you. Thank you. Thanks everyone. We're in the same thing here. You're doing the right thing. Stay on in this course. It's your long-term investment, and we'll be there. Any questions before we begin? No? We're good. Okay. Okay. Now we're sharing the screen. Perfect. And here we go. It's lecture 17 on applications of high-dimensional probability to different areas of data science. And in particular, last time, we started to discuss applications to combinatorial optimization. The problems in combinatorial optimization involve finding the best solution among finitely many, or not continuously many, but finitely many options. Just to be specific, we considered the following problem, which is hard problem. So we're looking at numbers, so given numbers such as interactions between the atoms, or interaction between stocks or something else, or maybe graphs, edges between graphs. We did that. So numbers, Aij. We would like to maximize the quadratic form Aij xi xj in X. Now here, if we allow X to be on the unit sphere, let's say, that will maximize the quadratic form on the unit sphere, and that is a spectral problem. It's easy to solve. However, if we would like X, if we require X to be discrete, such as plus or minus 1, the problem becomes hard. It is an NP hard problem, which is, informally, it says that there is you can't play smart here, right? There is no smart trick that would suddenly convert this problem to an easy problem and you solve it and you're happy. That's not gonna happen, most likely. It's really difficult. The difficulty lies in the set. The number of configurations of these xi's is obviously 2 to the n. Each sign can be plus or minus 1. There's n of them, so 2 to the n possible configurations. And the exhaustive search, if we just try them one by one, is this a maximum? Is this a max? Is this a maximum? That's not going to work. The computer will die before it reaches the solution, because it scales like 2 to the n for large n. Okay. So this is the combinatorial and NP hard problem. There is no common way to address these problems. There's NP hard problem, but you can ask, maybe you can solve it approximately. Maybe there is a good way to obtain an approximate solution, not maybe the perfect one for which you will work too hard, but maybe something of use. The common way to approach such problems is called relaxation. We relax it to a simpler problem. So we make a relaxation. Namely, it's called a semi-definite relaxation. Semi-definite relaxation of the problem to something that is simpler. Namely, we note that xi, xj, these are just a product of our variables. So if we call that, we change variables, call this Gij, or sorry, let's change it, Zij. Let this be our new variables. We achieve, first of all, we achieve an important thing. The problem stops being quadratic. The sum of Aij times Zij is now linear. That's already helpful. This becomes a linear problem, still combinatorial. And let's rewrite it this way. Sum of Aij, Zij. Perfect. And Z, the problem, the new variable Z, they become a matrix, n by n. Zij, I goes from 1 to n. That goes. So Z is our new variable is now a matrix. It's not a vector of xi's. It's now a matrix. Okay. What do we know about that matrix? We know, and we did check it, that Z is positive semi-definite matrix. That's one thing. We also know that the diagonal entries, Zii, well, just think, right? The diagonal entries are xi times xi. So this is going to be xi squared. Xi's are plus or minus 1. So the sign will be killed, and xi squared is always 1. So Zii, the diagonal entries are always 1 for any I. That's what we know about Z. And obviously, this inequality holds, right? Because going from X to Z, we enlarge the feasible set over which we take the maximum. And so that inequality holds. So that's called a semi-definite relaxation. This problem, the new problem, is, let's see, is linear. Linear in the sense, I'm sorry, the objective function is linear. And the feasible set, the set over which we maximize this one, is convex. So we are maximizing a linear function over a convex set. Let's say this is the level sets of that linear function. So how do I do that? Maybe I go down until it touches this point, and that's my solution. So it's kind of a geometric way to do this. Generally, it is a convex program. So this is a convex program, maximizing or minimizing a linear function over a convex set. That is something that you can put in the computer, and the computer will not die before it answers that question generally, right? It's a problem that can be generally solved. We think in data science, when we see the convex problem, we rejoice. We say, okay, convex problem, good. So at least there is hope. There are solvers for general purpose solvers for convex programs, even in MATLAB and Mathematica, whatever. In this specific problem is actually special because it is over matrices that are positive semi-definite. It's called semi-definite program. And there are specialized semi-definite solvers, commercial solvers, for example, for such programs that work a little bit faster by exploring the structure of the specific problem, semi-definite. So at this point, we relaxed the original problem, which is hard, combinatorial problem, to a convex program, in fact, a semi-definite program, which can be solved, extractable computationally. And so we can do that. Okay, so that's what we did. Now, of course, the question number one is always, how good is the relaxation? Right? Okay, we did that. There is relaxation, there is an upper bound. Is there a lower bound? Something like this, right? Or at least approximate lower bound. Is it any good? Because we can relax to whatever we want. And then how do we know we're still in touch with reality? That's question number one. Question number two is, how do we get the solution back? Even if this problem is very nice relaxation, what it spits out, the solution, is a matrix Z. how do we convert the metric Z into the signs plus or minus 1? That's another question, right? How do we relate solution to not just the value to the value of the objective function, but solution to the solution? So that's another problem. And we will actually address both of them. It's possible to do that. Good. That was last class. Any questions before we proceed? Yeah, good. Okay, just before we address these two problems, it will be convenient to rewrite the semi-definite program. Rewrite the semi-definite program. Let's call it SDP here. That one. The semi-definite program in terms of gram matrices. This is something, gram matrices is something from linear algebra that you probably have done in linear algebra. In any case, I put it in the new homework 6. So here's a definition or proposition, which is actually in the new homework, which is 6, right? It basically says that any positive semi-definite matrix is a gram matrix, and any gram matrix is positive semi-definite. So the gram matrix of a system of vectors in Rn just stores their inner products, Vi, Vj, for all I and j, which is a storage unit for storage for the inner products v1 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 v2 etc v1 vn v2 v1 v2 v2 etc v2 vn and so on. Well, you get the idea, right? It's just etc vn vn. Okay. But gram matrix, if you think about the gram matrix, it basically it defines the geometry, the pairwise geometry of the vectors. The diagonal of the matrix vi, that's a norm squared, so you automatically know the norms of these vectors, and you also, on the diagonal, also you know all of the inner products. And now from the norms and the inner products, you can definitely reconstruct, let's say, the distances between these vectors. So it defines all of this geometry, all of what you want to know about this vector. Okay. So first, the gram matrix is always positive semi-definite. Fact 1, you'll prove it, it's easy. Conversely, any gram matrix, any positive semi-definite matrix is a gram matrix of some vectors, of some system of vectors, v1 through vn. Okay, so that's your homework, and basically it says that positive semi-definite matrices, they're geometrizable. They have a clear geometric meaning. You can identify a system of vectors and you can look at these things geometrically. Perfect. Okay, good. All right, perfect. So how do we rewrite the semi-definite program here? Let's rewrite it in terms of these matrices. So Z are variable, kind of quasi-variable. The matrix Z is positive semi-definite, so it must be the gram matrix of some system of vectors. For some VIs. Great. The diagonal, as we know, the diagonal of Z That's the norms. So that's the inner products of vi, which is norms of these vectors squared. And the condition in the semi-definite program is that they be 1. Okay. So that makes an interesting story here. So really here, Zij is the inner product of some unit vectors that have norms 1. Okay, let's rewrite it. So the semi-definite program becomes sum of Aij, Vij, and the maximum is over all possible vectors that are unit vectors, so that have norm equal 1. Okay, that's our description. Why is this interesting? Why is it natural? Well, let's compare. Let's look at this beautiful thing. Compare this, the original problem, to its relaxation. What do we see? We see that relaxation just increases the dimension of the original problem, nothing else. Well, think of xi, xj. Think of these xi's, the original variables, as being one-dimensional vectors. One-dimensional unit vectors. What is a one-dimensional unit vector? It could be pointing into either to the right or to the left and has length 1, so it should be either 1 or -1, right? One-dimensional unit vector, +1 or -1. And that is the original problem. The new problem is the same, except in the unrestricted dimension. You just replace xi's by vectors and have fun with it. And that's semi-definite problem. Good. Good. Okay, so now what will happen next? It's a little preview of what happens next. We will relate these two problems. We already know that this is like less than or equal to, and we will prove that this is good up to with accuracy 90%, about 90%. So the lower bound here, yeah, the lower bound here also holds, but approximately. So it's like with constant something like 0.9. So like 90% accuracy, we can get that. And we can actually get the numbers back. So something like that. And we'll do it today in the next class. Good. For just simplicity of presentation here, it would be easier to work with one of the cousins of this problem. And remember, last time I described many different versions of this problem, and one of them was for max cut, finding the maximum cut of the tree, of the graph. So there is a graph, and you want to take scissors and cut through as many edges as you can. For that situation, the problem is a little bit, just a tiny bit different. Instead of xi xj, there is 1 minus xi xj, as we did last time. Just a version of it, but it will be easier to work out first. So let's do this, and this is the celebrated result on semi-definite relaxation of max cut. Established by Goemans and Williamson in '94. One of the benchmarks of theoretical computer science and data science. It kind of revolutionized the area of semi-definite relaxations. Okay, so we'll, like I said, we will work with the cousin of this problem, so the max cut. So if, let's say, G is a graph, and we would like to cut it like this through as many edges as possible. Like that. we look at the adjacent, Aij will be the adjacency matrix. Aij, it's 1 or 0, depending on whether there is an edge between vertices I and j. If I and j are connected, and 0 if not. Okay, so it stores this adjacency matrix basically stores the graph in a convenient way. That's how you store the graphs in computers. Just list all edges as a matrix. And the max cut of G is done as follows. Let me again explain how we mathematically write the max cut. We would like to separate the set of vertices, which is from 1 to n, into 2 classes. That's how we do the scissor thing. Cut them into 2 classes. One class will be labeled 1, the other class -1. The vertices in one class will be labeled 1, the vertices in the other class -1. So we put these labels xi's, which are either plus or -1. They define the labels and therefore the class. Perfect. And then we put the edges. We count the edges just between them. Okay, how do you do this? Sum Aij. So we sum the edges over this xi xj. Just okay, let's think. If xi xj are 1, so okay, if this is if they're in the same class, then xi xj is 1. Then 1 minus 1 is 0. So this will be 0 if I and j in the same class, correct? Because then the product will be either 1, 1, which is 1, or -1, -1, which is again 1. Okay, so that's 0. Or 1, no, not 1. So 2, 1 minus -1, which is 2. If I and j are in different classes. Yep. So each edge is counted twice because of that number 2. So I need to divide by 2. But more than that, actually each edge is counted 4 times because ij is counted twice because of the factor 2. And then there is ji. That's again counted twice because of the factor 2. So you divide by 4 to make that correct. That's max cut. Oh, I didn't put the max here. I should have. So it's 1/4, sorry, 1/4 times the maximum over all partitions. So over all label assignments. Assign labels, these partitions, the graph, and then you cut through that. Take the maximum. Okay, so that's max cut. Good. Okay, that's max cut. We would like to solve that problem. And we will do this just today. In like 35 minutes, you will see how to do this with accuracy 90%. Just totally surprising. It's crazy. I wouldn't believe it. Because it's a hard combinatorial problem. How can you do that? All right, so let's do this. Semi-definite relaxation. We know how to set it up. It's called semi-definite program, SDP, for the graph. We just replace just like here, remember what we did? We made this xi's, the original labels, vectors. Just allow them to be vectors. So instead of xi xj, I'll have inner products, vi, vj. The new variables are v now. And I take the maximum over all vectors that are unit, whose norm equal 1. Good. This is our semi-definite program. We can put it in the computer and solve it. Convex programming for matrices. Okay. we know it's a relaxation, just like before. So that's always true. Relax it. So the feasible set becomes larger. Maximum of a larger set is larger. That way it goes always. So we solve SDP on the computer. We can do this. And that would get us the vectors, VIs. The vectors V1 through Vn in Rn. This is 0, then this is, maybe it gives us vectors like this. VIs. The question is, how do we convert this back to the solution? X1 through Xn of the original problem. How do we convert it back to labels? You have now vectors, but I want the, okay, here's our labels. How, but I have the scissors. I need to cut it in two parts, right? How did it tell me which parts? How do we convert them to the labels plus or minus ones? Because then I can do that. Okay. Anybody has any wild guess? Like I
probably like choose some hyperplane in there and separate all these vectors. Like one side of the hyperplane is 1 and the other side is 1.
Yeah, well, exactly. Yeah, Evgeny, this is right. This is exactly what we will do. And so let me try to. How did you guess that? Why do you think it's a good idea?
It's like the first thought of how to like discrete these vectors into two parts.
Yeah. I would say it's like this. You have labels, plus or minus ones. These are one-dimensional vectors, right? There's +1, like this, and -1. They're opposite vectors. We were looking for these kind of one-dimensional vectors. We relax it to high dimensions, but we're still hoping, if everything in this world goes okay, we're still hoping that high-dimensional vectors will still resemble the original ones. So there will still like cluster in those directions, like plus one direction kind of and minus one direction. There will be kind of separation among them. They will resemble these opposite vectors. And if that happens, we can cluster them. Right? This is how we can classify them into +1 or -1. We just cluster them into classes. Maybe we do something very smart, like K-means clustering. Maybe we do something very simple, like Evgeny suggested. And right, why do we have to do something smart if we can do just simple? Just take a hyperplane and separate. So just cluster. So this is clustering. And what is totally crazy but works is a random clustering. In fact, we will choose the hyperplane completely at random, ignorant of the data. So I'll just choose that hyperplane at random. And of course, if the vectors are very, very tightly clustered, then it really doesn't matter which hyperplane to use. Right? There's a very, very tight separation. That makes sense. So we'll do that. So this is called randomized rounding. The process of conversion from vectors to labels is randomized rounding. We pick a hyperplane at random and assign the classes +1 and -1 like this. How do we pick a hyperplane at random? Well, it's best if we just use some normal random variable because it's nice. So let G be the standard normal random vector. So take a random vector in Rn, and we know it's rotation invariant. So its kernel, which is the level set corresponding to 0 set, that will be that. So we can then take a vector V and assign the sign of inner product with V and J. So in this picture, here's G, and everything to the right northeast corner will be assigned as +1, and everything here will be assigned -1 because that's the inner product is smaller. Yep. So very, very simple. That's our rule. So the algorithm to solve max cut becomes the following. First, solve this semi-definite program. Second, okay, so we solve the semi-definite program and it gives you the solution. VI, the vectors in Rn. Second step, do the randomized rounding. This is where probability comes in to play. Take the sign of VIJ. That's it. And then just output the resulting partition. So plus or minus ones. Output some partition in two classes. We already have the labels for them. So here will be the vertices I for which xi is -1, and here's the vertices for which xj is +1. That's it. Done. Then take the scissors and cut. That's it. Good. Whatever. Yeah, Goemans-Williamson algorithm. We haven't proved anything about it, but that's a proposal. Now the theorem, Goemans-Williamson, is that the expected cut, well, the algorithm is randomized. You understand that, right? Because of the G, because of random hyperplane. So it will succeed with high probability, but we can expect it to succeed just with probability 1. The expected cut, we take the expectation of the cut of this partition of the solution that is given is at least 90%. Wow. Actually, it's 8, 7, 8. That was too optimistic, but almost 88% times the maximum cut.
So this is an absolute constant that somehow arises in this proof, right?
The 0, yeah, that's exactly the absolute constant that arises in this proof. Yes.
Looks weird.
It's weird, yeah, but it's so close, 90%. In fact, people have proved that this problem is not only NP hard, but it's impossible to approximate. So you can't improve that constant to an arbitrary constant close to 1. There is some threshold. There is some information, not information theoretic. Sorry, there is some threshold where the problem becomes NP hard. We do not know where it is, but you can't expect this. Like to get smarter and smarter and get closer and closer to 1 and get arbitrarily close. No way. Somewhere it will be hard wall that you can punch through.
And some deterministic like clusterization of those vectors that makes like the approximation better or not?
Yeah, that's a great question. It's okay. We haven't proved, but it's a very silly way to cluster, right? It's the silliest clustering method ever available. Just take a random cluster, no look at the data, just do it blindly, just smash through, just cut it through. Who does that in practice? You would hope that by getting better clustering, k-means, to something much better, you can improve this. But in fact, I think this is the best known still. It's, what is it, 30 years now, and this is no one can improve it. So maybe in practice it gets better a little bit, but overall, we don't know. Theoretical bound, this is the best possible for now. It's a great question for you guys. Maybe we need some fresh ideas here. 30 years, people are tired about this. Okay, so here's how we go. Proof. Yeah, any other questions? Okay, proof's going to be beautiful, totally. So you'll have a lot of fun. Okay, so what's expected cut? Expected cut. Let's look here. Well, that's what cut is. The cut is this. So I'll just write it down. 1/4, which is a prefactor, times expected value of 1/4. And then I'm just rewriting this form aij 1 minus. In fact, I pointed to the wrong thing here. This is the expected cut of the algorithm. So it's 1 minus xi xj. So xi xj. And remember, xi xj are the output of our algorithm. Okay. So first of all, let's move the expected value inside by the linearity of expectation. The only, well, everything is deterministic here except xi xj. So the expected value is moved to the random part like that. Good. Now we remember how we got xi's. Where did we get them from? That's from randomized rounding right here. So this is expected value of the sign Vij, sign Vj, G, not J, G. So far, so good? Yeah, I did nothing here. I just wrote what we had. Okay, can we compute this? It should be a simple problem. Vi and Vj are now fixed vectors. Just fix two vectors. And then fix two vectors like this. And then there is a random hyperplane. Just put the random hyperplane like this, or maybe like this, or maybe many positions. And what is it that we want to see? Well, this could be either plus times plus. The expression can take two values. 1, again 1, or minus 1. It's a very simple random variable. It takes two values, 1 and plus and minus. So probably you can compute that thing. And when you do this accurately, and this is actually a homework problem too, you get the beautiful inequality that was first observed by Grothendieck, Alexander Grothendieck. Grothendieck's identity, actually. It's an equation. Generally, for any two unit vectors, u and v, if g is a just random normal, then the form that we're looking at, random thing g, equals, okay, now it'll be a little mystery, but I'll demystify the right-hand side, equals 2 over pi arcsine of the inner product, u and v. Okay, a little weird. Let me explain what's going on here. Let's do a quick idea of the proof, and the full proof is actually in the homework. Oh, first of all, is the statement clear? Yeah, two vectors and then g. Okay. Cool. Okay. So proof, beautiful idea. G is rotation invariant. Rotationally invariant. It means that its direction is completely uniformly distributed. All directions are possible. So this means that without loss of generality, WLOG, without loss of generality, we can think of U and V. There are two vectors in Rn. So we can just rotate these two vectors and put them on the plane, R2. Right? Generally, these two vectors are like this, right, in the space. But G is rotation invariant, so I can just rotate all of that picture and put these vectors on the plane, R2. This makes the entire problem two-dimensional. It's not a problem about n dimensions, it's a problem in 2 dimensions. And you can just put it on the computer in the MATLAB, let's say, or something like this. So G is now normal vector in R2, so 2-dimensional. That's observation 1. Observation 2. The sign does not care about the norm of G. It only cares about the direction of G. Right? The length of G, if I multiply G by 5, what happens to the sign? Same thing, right? So that I can replace, so the sign is independent of the norm of G. And so instead of G, I can replace G by normalized version of it, G over its norm. And the left-hand side doesn't change. But what happens is that this thing, what is it? What are we looking at? We take a normal vector and then normalizing it. Now it's a unit vector. And what is its distribution? What do you think? G was rotation invariant. And now we are putting it on the sphere, right? So we contract, dividing by the norm. So now it's on the unit sphere. And what is it then?
Uniformly over all angles.
Exactly, it's uniformly, right? Because all directions are the same probabilities. Now it's uniform. So this vector, theta, let's call it, it's uniformly distributed on the sphere in dimension 2, which is a circle. Like this. So theta is uniformly distributed in the circle. And we have two vectors, U and V. And theta. And this becomes just a calculus problem, I guess. For theta, there are some directions for which the left-hand side will be 1, and some directions for which left-hand side will be -1. And you just identify the portions of the circle and compute the length of that arcs, and that's it. And when you do this kind of high school trigonometry, then you will get to arc sine. So that's going to be your homework problem. It just becomes a trigonometry problem in the end. Okay, are you good with this general, like a leap of faith here, or kind of? Let me show you one more thing. Okay, so if I take, let me think, if I take, I'm trying to identify the areas for which, the areas of the circle for which the form will be +1 and for which the form will be -1. So this is U, this is for V. I'm doing the orthogonal kind of hyperplanes. I think here the form will be, hold on. Yeah, I think this, here the form will, okay, here's one will be U plus, one will be minus. This is negative, I think. -1. This will be -1. Here it will be +1, and here it will be +1. Yeah, imagine if theta is here, let's say, then theta will have positive inner product with U, but negative with V. So you'll have you will have plus 1 times minus 1, and the form will be negative. And you just analyze the other parts similarly. And because theta is uniformly distributed, take an expectation is just computing, is equivalent to computing the length, how much. And you can compute that length from trigonometry. Good. Okay, so that's Grothendieck's identity. Simple one. All right, let's go on with this. All right, where have we left off? We left off here. Right there. So I'm continuing our journey. Continue our journey. So we get 1/4 sum Aij, and here we have, I'm doing Grothendieck's identity, 2/pi arc sine Vij. Yeah, like that. Okay. Well, that's arc cosine actually. So it's if you think about this, I think it's just arc cosine. 2/pi arc cosine of Vij. Okay. Now, what if we didn't have any arc cosine here? If this was like Vij or something like that, then we will be back to the semi-definite program. And that's what we wanted, right? We wanted to relate the expected cut solution to the solution of the semi-definite program. So if we didn't have that's annoying nonlinearity here, the arc cosine, we'll kind of win. That's almost where we want to be. Yeah, so we're almost there, except of this arc cosine, which ruins this thing. So.
Maybe not exactly, because we have this problem with 1 minus, like in product of Vij.
Yeah, maybe not exactly. Okay, maybe, all right, maybe we should have stopped here, for example, right? So if we didn't have arc sine here, let's say, then we will be fine, I guess. Maybe, okay, maybe it's like 2/pi, but if we remove that, right? If we didn't have that annoying thing, then we would have exactly the solution to the semi-definite program. And then we will win, because we'll say the original problem is exactly a semi-definite. So there is like a two-way road. Solve the semi-definite on the computer and get exactly the cut, 100% accuracy. Okay, so we have to deal with this thing somehow, with the nonlinearity. What do you suggest? How do we deal with nonlinearity?
We say that it's almost always very small and linearize.
Yeah, exactly. Yeah, perfect. Yeah, linearize, exactly. Maybe it's always very, very small, like Vij. So there are arc cosine. Yeah. Okay, let's try to linearize. I'm not sure how small it is, but let's linearize. Okay, this is arc cosine. Sine, arc cosine. So cosine takes value between -1 and 1. And then 2/pi. So if this was pi, this is 2. And I think that's what it does. Oh, okay. Can never draw this perfectly, but something like that. That's just part of the wave. That's arc cosine on that interval. And we want something like, let's see. Now we have to be a little bit careful. I have 1 minus this, 1 minus. So I want to linearize it at this, starting from this point. And my linearization should be like this, maybe. No. Yeah. Okay. -1, 1. Let's linearize it this way. Linearize. And I did this offline. I actually checked it on MATLAB here. So 2 over pi arc. Oh, first of all, is it clear that I want the lower bound? Yeah, because we want to create as large cut as possible. So I want to create the expected cut that is larger than 90% of the max cut. So that's the direction I'm going. So I need to lower bound. Okay. So I get arc cosine of theta is greater than whatever, 0.878. That's where I get this 90% of 1 minus theta. 0.878, 1 minus theta. Except I messed with the colors, didn't I? Color this one. Okay. So that's this picture. Okay, good. We're almost done. So now we're lower bounding this by 1/4. Okay, I can take this 0.8 thing out. 878 times 1/4 aij 1 minus vivj. Yay! And this is our semi-definite program, the original one. Oh, gee, done. Why done? Well, the semi-definite program, of course, it's larger than max cut because it was a relaxation of max cut. So we get 0.78 times max cut. Oh, gee. We're done. Any questions? Observations, comments, objections? A brilliant and a very simple argument, if you think about it, right?
So apparently all we use here is the linearity of matrix expectation and this approximation for cosine. Yeah. So like
Okay,
no complicated things.
The first part of your phrase, I didn't catch that. Can you say it?
So we use here only the linearity of expectation and this approximation of our cosine, nothing more. Yeah.
Nothing more. Nothing more, just that. And yeah, I guess a natural question would be if you do something smarter than just this trivial clustering of vectors. Maybe you can do something better, but no one knows. No one succeeded yet in doing that, which is weird. Yeah, just that. Good. Yeah, this is just a starting point. Obviously, you can. It's a very general method, right? So you just replace these labels that are combinatorial. Combinatorial problem replaces labels, plus or minus one, very difficult to handle labels, by vectors. By vectors, and then you have semi-definite program. Solve semi-definite program and then do the just randomized rounding to go back. In practice, people don't do that. People actually do clustering that is better than just randomized rounding. For example, the k-means clustering. And you do see that vectors really are clustered like that. So this method produces better results, I think, than the spectral clustering would in practice. So that is the idea. Good. So that is one thing. The other thing that we will do next time now is we will go to the original problem. This versus this, without one minus thing. And we will show that, well, first of all, it's clear that this is a relaxation, so it's smaller than. But we will show for that problem too, that this holds with accuracy. 1 divided by 1.7. I remember the other constant. So 1.7 will be the constant that's in front. So 1 over that. So it's not as good as semi-definite. And again, no one knows better. We will not show how to get the solution back to the solution, but it's very similar to randomized rounding. It's another randomized rounding trick. Maybe I'll put it in the homework. So my point is that any problem that you see of that nature you can hope to work it out. Hope to work out the semi-definite relaxation for it. And this has been very popular in the last 10-15 years. Semi-definite relaxation of combinatorial problems. Whoa. Good, I'm done. Any questions? More questions? Cool. Okay, guys, I'll stay here for 10 minutes or so, maybe 15 minutes. If you need me, I'm always happy to talk about everything. Oh, and most importantly, tomorrow, same time as this class will be the meeting with one of our researchers. I'll send a reminder in the email, but please remember to come tomorrow. Anybody interested? And I'll stop recording now.